Hello and welcome to Toddcast 36. Hopefully you've seen Toddcast at least 34 and 35, the SN1 and SN2 reactions independently, and learn the nuances of them. But this Toddcast 36 is going to put all the information together and be our introduction into how you make decisions when faced with a question on like an exam or homework or some scenario academically, what it's going to be. So want to start by building a giant chart. This chart's going to slowly fill in. I know there are 9 spots for the whole area. I'm going to end up using 3, 2, and 3, so 8 to compare one to the other. So one of the big decisions you're going to have to decide is first off, is it a nucleophilic substitution reaction? And in general, look for a nucleophile, check, and look for a leading group on a carbon. If you have both, then it's going to be an SN reaction, nucleophilic substitution. And whether it's pathway 1, SN1, where the leading group first leaves, or SN2, where they come together, that's going to be decided based on the following. So we choose SN2, nucleophile will attack when it's not very crowded. So primary, better than secondary, better than tertiary for the electrophile. So that's going to be the very first thing we look at. Methyl should be ahead of this, and then primary should be better than methyl, but I'm going to leave methyl out because that's just not a very realistic scenario. We generally aren't going to react on methyl carbons, going to react on carbons in bigger molecules. Okay, so if it's primary, it's SN2. If it's tertiary, it's SN1. When it's secondary, could go either way, so we need to consider other factors. A good nucleophile will have a tendency to force its way on, so SN2. A good leading group, SN1. But if you have a scenario where you have both a good nucleophile and a good electrophile, a good leading group, then again, it's going to be a toss-up. And so our last deciding factor, it's a solvent. We haven't really focused on solvent too much, but aprotic solvent needs to be polar because it has to stabilize delta plus, delta minus in the transition state, but it cannot be protic, otherwise it will actually bind and hinder the nucleophile, and will bind and impact the leading group. On the other hand, for SN1, because you do want the leading group to be pulled off, a polar protic solvent, a hydrogen bonding solvent, can actually bind with the leading group, and in doing so, pull it away and weaken the leading group bond to actually help break it. But a lot of times it'll hinder the nucleophile coming in because the nucleophile will now be hydrogen bonded to the solvent, and when it moves through, it's going the solution is going to have to drag along all the solvent. But let's consider the impact of solvent. So this is a reaction. You'll see something like this in pretty much every textbook. They like to look at the simplest case, methyl iodide. In some instances, maybe ethyl iodide, but something very small and easy to monitor. And so we're going to add some nucleophile. It's going to come in from the backside and kick the iodine out. No chiral center, so no way to monitor that way. You just have to monitor the appearance of the product, whatever that new bond is, if you can monitor it over time. Okay, so everything's going to be relative in this case to the reaction of chlorine nucleophile with methyl iodide as your electrophile, so iodine will be the leading. And so, as a result, we're going to have a table of various nucleophiles. We're going to do it, the reaction in a protic solvent and an aprotic solvent. So methanol, one of your more common protic solvents, it's an alcohol, hydrogen bonds. And then dimethyl sulfamide. So this aldehyde group on a nitrogen, which has 2 methyls. All the H's are in carbons, so it's not hydrogen bonding, but it is relatively polar. And so we're going to have, they're both being polar, but protic and aprotic. So we're going to look at the ratio of how fast it is in the aprotic condition compared to protic condition. So SN2 versus SN1. Now I know this is going to favor an SN2 reaction, so aprotic should be faster. So if we want to compare, this is our baseline. So again, methanol is my solvent and Cl minus is my nucleophile. That's why this is a 1. That is, everything's relative to 1. It tells me that it's about 1,000,000 times faster when done in an aprotic solvent. So if we do iodine, so this one's going to be tricky. To monitor it, you have to put a isotopic labeled iodine. So if we use iodine in this reaction instead of chlorine, iodine's a better nucleophile than chloride. So consequently, when I use that, it's about 1,000 times faster than it was with chlorine, but it's about what, 6 times, about 6 times slower when we use the aprotic solvent. Notice the relative ratio is only about 100 to 1, whereas this was 1,000,000 to 1. So you start running into incidences. So we want to figure out why that would be. And so let's look at the rest of the table and then come up with some reason. So Br, we start to see a trend. So Br minus, when we use that as our nucleophile, it's only a little bit faster than chloride in a protic solvent. It's about half the speed or so in an aprotic solvent. So these actually are starting to get close to one another. Then finally, fluoride. Fluoride is so small, you'd expect to be a great nucleophile, but apparently it's really slow. And that's because of hydrogen bonding. The methanol can form a hydrogen bond. Hopefully draw this in a good way. That's not going to work. Let me redraw it. I did not full screen. So if I do that, this hydrogen bond can form there. And so this fluoride is not just moving in and attacking there. So it's not just coming up and going there. This entire thing has to go up and go in. It's got to drag the solvent along. That actually hinders it. So notice that in a protic solvent, iodine's a better nucleophile than bromide. Bromide's better than chloride. Chloride's better than fluoride. But when you reverse it to an aprotic solvent where you do not have any hydrogen bonding slowing it down, notice the rates are much faster in an aprotic solvent than a protic solvent in every single case. And on top of that, you also have fluoride is the best nucleophile in aprotic, worst in protic. Because of the hydrogen bonding interaction with the solvent, it hinders, the smaller it is, the closer it is in orbital size, the better it's going to overlap, the more it's going to interact with the solvent, be hindered. Aprotic solvent, fluoride being smaller, is going to be a much better nucleophile. Also, HI is a strong acid, meaning I minus is stable. HF is a weak acid, so F minus actually a little more reactive. So it's more reactive, so it's going to be faster, and the solvent doesn't hinder it, so it's going to be faster. So this tells us then that in a protic solvents can actually hinder your nucleophiles. Aprotic, they don't see that effect. So it's straight nucleophilicity. Here, it's nucleophilicity hindered by solvent, whatever way the solvent hinders it. There's a lot of information here. This is a thought-provoking scenario where fluoride is the worst in protic, but the best in aprotic. So when we say what nucleophile is the best, we go back to the table we had in Toddcast 33. That table is based on an aprotic environment because actually semi-protic, I should say, environment, because it gave I as the better nucleophile. That's why those lists are not the best to consider, because as the size starts changing, the solvent starts changing, the numbers change. So the key thing here, protic solvents will hinder things that can form hydrogen bonds or water interactions, H interactions. And aprotic does allow us the true nature of the nucleophile to come through. Okay. So the point being, in an aprotic solvent, SN2, your nucleophile is unhindered, so it can come in. SN1, nucleophile is going to be hindered, so therefore, if you use a protic solvent, you bind that nucleophile, it's not as good, so it's going to have to wait till leaving group leaves, and it's going to be more likely to go by SN1. So SN2, primary, with a good nucleophile and an aprotic solvent. SN1, tertiary, with a good leaving group and a protic solvent. Okay, the during. During the middle of this, you have 5 things attached. Again, 2 are monocheeking, 3 are fully bonded. This one, you lose a group, so there's only 3 things left. You have a planar carbocation. Bond angle drops to less than 109.5. It drops all the way down to 90 between the nucleophile and the 3 groups that are going to remain. And then in SN1, the crowdedness to begin with of bulky groups are going to start repelling one another and push it out to an sp2 or trigonal planar intermediate, so that sterics actually helps push the leading group off. So I want to consider again the two reactions. When we have a primary CH3 on a carbon, these are H and deuterium, so these are isotopically labeled, but they're still hydrogen chemically. So one other carbon, so primary, so it's going to be an SN2. As it goes on, you're going to have it partially bonded on cheek on one side, partially bonded on the other. So we typically draw the bracket around it in this little double dagger to represent a transition state, and negative for the overall charge. So you have a partial negative here, partial negative here, shared between those two sides. And then in the end, that's going to come on and kick out the BR. Okay. The reason we put a deuterium on there is if we wanted to do RNS, then we say priority 1, 2, deuterium is 3, H is 4. So when you have the same atom, you go to atomic mass in the priority list. So 1, 2, 3, starting as S. 1, 2, 3, 4, finishes as R. So you get inversion chirality. SN1 reaction. Again, want to start with the chiral center to monitor it. Leading group leaves. We have a tertiary carbocation, which is stable, so we won't get rearrangement. We've been over this at some point. A nucleophile is free to attack from the left side or the right side. So if it goes from left, it goes to one side, goes to right. And we actually, just point of interest, could actually use FC3, F3COH to come in and deprotonate at the end. I've chosen the negative for this. Acidic and basic conditions will dictate exactly what the state the nucleophile is in, but I went with negative. Doesn't have to be negative for this reaction. Because when you have a negative and positive, it's kind of hard to have both in solution at the same time. Protic solvent will help that. Okay, so it comes in from the left, comes in from the right, which means you get chirality of 1, 2, 3, R, and 1, 2, 3, S. So 50-50 mixture of R and S, racemic product mixture. And in the end, the product features. You get one single enantiomer. R turns into S, S turns into R, you're set. Whereas for SN2, in SN1, you get a racemic mixture. You might even get some other product caused by rearrangement. So SN1's a mess. SN2 is a very clean, pure single product. Second order rate, very fast. The rate depends on nucleophile and electrophile both. For SN2, SN1 only depends on electrophile, much slower reaction. And then SN2 goes in one step. So the 2 means two things. So it's second order. The 1 means one thing, so it's first order. So the number is based on the order, not the number of steps. So just note that the number is based on the order, not number of steps. So SN1 is 2, it's a 2-step. SN2 is a 1, it's a 1-step. And the energy diagrams, you definitely have to recognize. They're pretty typical. So reactant goes up to transition state, where you have the 5 things attached and finishes as the inverted product. SN1 leading group leaves, rehybridizes to a stable carbocation, goes up to the second intermediate as nucleophile comes in, until it finally forms first stable product. Okay, so question-wise, this is hopefully an area where you turn off the or hit pause for a moment, do the question, and then come back. So assuming you've done that and you're back, which change to the reaction will result in a change in the nucleophilic substitution mechanism by which it proceeds? Translation, which one just converted it from either SN1 to SN2 or SN2 to SN1? So systematically, we're going to look at each of the answer choices. So for choice A, we have a tertiary electrophile, and we're changing the solvent from methanol to acetone. So we're going from a protic to aprotic solvent. So protic favors SN1, aprotic favors SN2, but tertiary, it's going to be SN1 no matter what we do. Changing the solvent is just going to slow it down, but it's still going to be the SN1 mechanism. So also go through the carbocation. Going to jump to D because that's the other extreme. In this case, we're dealing with a primary alkyl halide, And we're talking about alkyl halide with high versus low bond dissociation energy, meaning a good leaving group versus a not as good a leaving group. Again, irrelevant. SN2 is going to be associated with primary. So primary electrophile, no matter what we do, still going to be an SN2 reaction. So it's B and C we have to consider. In each case, you're dealing with a secondary. So in choice B, secondary, you're changing from a good nucleophile in ether to a good nucleophile in ether. So knowing what these are, so this is ET2O, meaning ET group on oxygen connected to an ET group in ether. Ethers are aprotic, all the hydrogens are in carbon, and they're polar. So polar aprotic, exactly what we need. THF is also an ether, just cyclic. So these are your two solvents. So changing from one ether to another ether and having a good nucleophile in both cases. So it's going to be SN2. Both nucleophiles are good. So SN2, both solvents are polar aprotic. So SN2 no matter what, not going to change anything. Finally, this one better work out. So it's secondary in each case. One case, it's a negative in ether, so a good nucleophile in an aprotic solvent. In the second case, it's an okay nucleophile, but we're no longer in an aprotic solvent. We just have it is its solvent. So definitely SN2 conditions for this. This one, I should try to change colors. This one's going to be more SN1 conditions because it, although it doesn't hydrogen bond, thiols are on the brink of it. They have very slight interaction, and it's similar to, like, energetically similar to a hydrogen bond. So this one is going to be impacted by going from a good nucleophile to a bad nucleophile, to go from a aprotic solvent to not an aprotic solvent, or a semi-protic solvent, or I need to come up with a word for that, but that's the only one where you see a change. Okay, tough question, but good summary of everything. Okay, so the last thing I want to emphasize, the leaving group. So alcohols are just such a prevalent compound that we use them as our starting materials in a lot of reactions. So we have to turn the alcohol into something more reactive. The OH is a terrible leaving group. I've arbitrarily assigned S stereochemistry. I could have assigned R. I'm just doing this for reference. So if we have an alcohol that starts out with S, if you protonate it, so let's consider change this to, sorry, did not mean to change color. Okay, so there's my alcohol. Let's double check S. Ready, 1, 2, 3. So 1, 2, 3. Clockwise, but H is in front, so this would be S. So sure enough, there's my S. If I protonate it, turn this into H2O plus, this carbon is still going to be S. Priority is still 1, 2, 3. So changing the OH into OH2, making it water with a plus charge, didn't change chirality. So you end up with ROH2 plus. Okay, next on the list is tosyl chloride. Tosyl chloride is going to act an awful lot like H, except now it's going to form a bond to something called tosylate. And in doing so, you actually deprotonate that H. So you have something called OTOS. This chiral center did not change. It's actually a chiral center. So OTOS with S chirality and then methyl chloride, very similar. You do not have to necessarily memorize the compounds, but you have to recognize that they react with the O. Protonation, tosyl chloride, and methyl chloride react with the O. For the next grouping I'm going to add, this one does something a little bit different. So here, let me go back to drawing my molecule over here. I have my HC3C, my CH2, my H in front, and my OH here. With PBr3, weird as this may be, O is going to attack the P, just like everything else. So it seems like it's going to, in this case, just be the same old thing, make it S, but it's going to knock out one of the BRs. And so it's going to turn into, once it attacks, PBR2 with the BR minus. And so the BR minus is going to come back and kick it out by way of an SN2 reaction. So now we're going to have the same structure as before as far as the skeleton goes. I'm going to try to fit it in. So let me try to be a little more careful getting this to fit in. This H is now going to be in back, and your BR is in front. So now 1, 2, 3, H is now back. It just went from S to R because of that inversion. So you end up getting chiral inversion. And if you use SOCl2, it's going to be a similar thing. Kicks out this oxygen attacks the sulfur, kicks out the chlorine, which comes into the backside and knocks it out. So the reaction mechanisms, you can know them, but when I have an alcohol, I can turn it into a better leaving group in a couple different ways. Protonate it, tosylate it, mesylate it. That just doesn't, nothing changes. But if you use PBr3 or SOCl2, then I can actually convert OH into a BR, OH into a Cl, but through this backside. Note then, because it's going by an SN2 reaction in both cases, these can only work with primary or secondary. You cannot do this with tertiary. Okay, so here's why I care about that. Let's say I started out with a secondary alcohol with S chirality. If I use PBr3, it's going to turn into an R alkyl bromide, just like it just did. And then if I add, let's say, a nucleophilic SANA group, CN minus is going to attack it and again go by SN2. So it's going to go back to an S compound. So I converted S to an R and then the R back to an S. If I want an S product in the end, but let's say I wanted an R product in the end, but OH is a bad leaving group, I could use methyl or methyl chloride, tosyl chloride, or just protonate it. If I do that, it retains its same chirality. And then I add KCN and it inverts. So I end up with an R. So you can actually target what chirality you want by changing the OH into a better leaving group by one of two means, with inversion or without inversion, which ends up in an overall inverted or overall not inverted product. This is one of those synthetic logics. So you have to understand where it's going to react and which side it's going to add to. And so this is the first of many cases where we'll have something called stereoselectivity. We choose one stereoisomer over another by some pathway. So that summarizes SN1, SN2. That's the first of the really common reactions you're going to see the rest of your time in OChem. And hopefully, little by little, the more questions you do, the more clear it becomes. So thanks for tuning in, and I will see you in the next Toddcast.